This morning, we want to look at using climate or meteorological data to help farmers along to improve the yield, as it were. And as we are aware, climate is very important, and so too is agriculture, as we would see as we go along. This is basically the layout of the presentation. I'll give you a little background. We're going to look at some of the objectives of the presentation. We'll look at some climate elements and so on, the potential impacts on crops, and we'll look at a simple weather station that you can put together. And I did go looking, and I found some that could be purchased off the shelf at reasonable prices. And we'll look at the availability of climate data for agriculture in the region, and we'll look at accessing this information. One of the objectives would be to identify weather and climate elements that are important in agriculture. We'll also look at some of the potential impacts of weather and climate on agriculture. We'll look at some DIY components for a simple weather station that you could put together. And we'll identify available data sets and suggest ways in which they could be accessed. Agriculture in the Caribbean has remained important from historical times, if I may put it that way. Agriculture has been important from slavery and subsequent to slavery, when there were small household units getting involved in farming for food security reasons, and then we had the bigger plantations. And today, that same system has come down, or it has been inherited. We still have large plantations, perhaps not as large, but they're still large by comparison to the household sizes. And it still remains important for many reasons. It's a form of employment for persons. It's a livelihood. People earn a living from it. It's food security, especially on the national scale. It's a foreign exchange earner, which is very important. We are unable to buy goods and services without foreign exchange. And basic subsistence. Some folks get involved in agriculture just to be able to, have food on the table, so to speak. Agriculture in the region right now ranges between 1% and 17%. In the case of Haiti, it's 17%, and Montserrat is less than 1%. And I'll show you a graph subsequently. It's employment of persons in agriculture range between 10 and 25%. In Haiti, it increased quite a bit.
That will be understood. So you can't just say, we never looked at it. Part B.
This graph depicts various countries on the scale of agriculture and its contribution.
During the recommendations part B, and we're going to, do our own thing or implement it our own way. But reference to those materials is mandatory importing.
Agriculture and GDP. So we can see Haiti on the upper left there as being at 17%, and the Cayman Islands we have here, but Montserrat is much lower than the Cayman Islands, or just about the same. And we see on the x-axis there is per capita GDP, as it were. Meteorological data in the Caribbean has been used from the early 1900s, perhaps late 1800s, through the 1950s for shipping, aviation, and plantation. And it's only in the 1970s when real value was seen in meteorological and climate information, after the World Meteorological Organization had done a climate change study, I think one of the initial ones, and realized that our climate was changing. Some of the sources of meteorological data, we have CIMH, or the CMO, National Meteorological and Hydrological Services. We have UWI, 5Cs, and there are some other repositories around the region which source their information from some of these that I mentioned and keep it. Today we have climate and climate data being readily available through the internet. We have rapid transfer systems such as automated weather stations and satellite information. We also have to use climate models to provide information for us. We could get some historical as well as projection data. And we have regional and national archives, which we could source information from. And we have national and other specialized publication to which we could refer. Meteorology and, like I said earlier, met data and climate data are important. It helps us to understand the variations in climate that exist across countries. Even from country to country, even though we live in the same large region, as it were, or some may say small region, our climate differs slightly. On a general scale, we are pretty much in the same, but there's what you call microclimates that exist. So it gives us valuable insight into weather and microclimates affecting farmers' area, lands, or the plantation. So even though you may, the Met Office may give information for a particular location in the country, it doesn't necessarily mean that other places in the country would experience the same kind of thing. And I'm certain you would say the Met Office said there was rain and you didn't get any rain. That's a good example. Weather information is also useful as an input data in crop modeling for various research applications to improve food security. And this is what it, these are some of the factors, the major ones in weather and climate. We have temperature, rainfall, wind speed, relative humidity, solar radiation, and atmospheric gases. So this is what it looks like in terms of how stuff feed in. We have rainfall and solar radiation and wind affecting, for example, evaporation, and I would give a little bit more on that. And we have atmospheric gases like carbon dioxide, which is useful in photosynthesis and also for your overall crop yields. For temperature across the region, we're looking at the first three bars, first three lines at the top. We have maximum temperature in red, and the blue is the minimum, and then we have in the purple, that's the average. And as you can see, our temperature doesn't change much. The average is about 27, 25, 27.5 thereabout. And you can see we get up to somewhere around 32. Seldom you would see 33 and so on. That would be an extremely hot days. And sometimes we see on average maybe 20, but in some cases when they're very cold periods in the north, we would see sub-20s temperature and so on. So temperature is very important for agriculture, because as we would see later, temperature and wind would affect evaporation. Just give me one moment, please. I am looking for something I want to refer to. Right, so the importance of temperature lies in its value in the end when it's improving yield. For example, for some crops, they would need higher temperatures to maximize yield. And for other crops, they would need slightly lower temperatures to maximize yield. Other crops, it really doesn't matter. For example, the crops that we grow in the Caribbean generally has a tolerance for the temperature variations that we see on the screen here. So it's not a big issue. In previewing the questions, and I hope this will address one of the questions, one of the reasons why temperature is important is what we are seeing here. When we look on the impact on yield on the right-hand side in the final column there, we see if they have changes in temperature. If we look at the center column of temperature changes, we see just about, if we add 2 degrees Celsius change in temperature, we could see that there are double-digit changes in yield for, we have beans, rice, and maize on the first column. So for these, we would see these types of adjustments or changes or fall in yield when temperature increased by the amount shown here. So that gives us an idea of how temperature or why temperature is important as it relates to these crops, for example. This is from a study in bellies, sugarcane and citrus. And we have a 1 and a 2.5 rise in temperature, and we see that there's a change with a 12 to 20%, 12 and 20% change in precipitation. We see the results of a 12 to 70% decline in yield for sugarcane and a 3 to 5% decline in yield for citrus. So this brings out how important temperature is. For rainfall, this gives us a general idea of what rainfall looks like across the, largely the insular Caribbean. It may look slightly different for Guyana and Suriname. This is the bar graph here gives you an idea of how the rainfall changes over the months. As you can see, in our dry season will be somewhere between January to April, and thereafter we would have the transition month of May into the wet season, and we tend to have a slight bump around the May, June, and then another bump around September, October days. So we have a bimodal rainfall trend, as it were. And this is what it looks like away from all the clutter of the other things. So this tells us that in the first couple of months of the year, we would pretty much be plants maybe just near water stress, and in the latter months of the year, the plants would probably be well off. In some cases, if it is a La Nina year, we may be experiencing a lot of rainfall, and plants may get into maybe experiencing some water logging and so on, some of the impacts that I will talk about. Right, and this gives you an idea here of the number of rainfall days across the region, and we can see it's not the same for every country. Some of the countries in the lower Eastern Caribbean have 200 odd days in a year in rainfall, and it's reflected in the rainfall totals in the northern. And I think for those of us who know our agriculture, we already know that islands from St. Kitts going up the road would tend to have a slightly drier climate from islands that are south of St. Kitts, as it were. Now, for some of the potential impacts on crops with respect to rainfall, we would have water logging if you have too much rainfall, partial submergence if you have flooding, or complete submergence for that matter. If you have too little rainfall, you're likely to experience decrease in moisture, and this would reduce crop production, and it would also give rise to pest infestation and so on. So those are two of the larger impacts that we would experience if rainfall change either way. This graph you're looking at on your screen here gives you an indication of when you look at climate data on a very long term, as it were, I'm using here in this case SPI3, which is looking at it over 3 months on a moving average kind of scale. Then we have SPI6 on the second one and SPI12, and we could see some areas in red, and those are the areas that, those are the periods that were dry, and the one in blue, the ones in blue are the periods when it was wetter. So we see, if we look at the SPI12, we could see some long periods of wetness and some long periods of dryness. And this, again, if you use climate data and you use long-term trends, you could actually see a pattern in periods of wet, periods of dry, and that could inform you as to whether you would put more into cropping or less into cropping during that period, depending on what you cropping for, as it were. So in drought years, you may not want to invest a lot. You may want to retain some of your investment for, for dry years, you may not want to invest a lot, but for wet years, you may want to put a little more into it because you know that your yields would be greater. And we know from the, when you are as an avid or an ingrained farmer, once you see there's a meteorological drought, you're setting up, because the transition between meteorological drought and agricultural drought is a very thin line. It has been observed in our region that we don't even have to get to 1 on the SPI scale for impacts to be affecting agriculture. We could be sub 1, you know, and we would be experiencing a pattern of dryness which would affect agriculture. Once it becomes very severe, you are going into hydrological drought, and then things like irrigation would become a problem. And these are some pictures that give you some indication of what happens during a drought. Your corn crop would dry up, you would have animals dehydrated, and so they would die. If you have excess water, you would have root rots, as you can see here in the bottom lower left, or you would have swamping here, in which case you see the vegetation there drowned in water, as it were. Wind speed is another category that is important. And in the Caribbean, our wind speed is relatively stable, except for when we have systems coming in. And those are the things that we need to be aware of. Over the years, from my experience, we would not receive at the meteorological services, then we would not receive a lot of calls about inquiries of wind. But when you have these outlying systems, seldom in a tropical wave, but sometimes you can, you will have farmers calling us, for example, a microburst. If we experience some thunderstorms, the downdrafts could have wind speeds that are very high, and then you would have some microclimate where you have winds in excess of 30 miles per hour, and you would have crop damage. Wind is also important in terms of aiding evaporation. So if you have high wind speeds, and sometimes in the Atlantic you have high pressure developing, and we have high wind speeds lasting for very long times, you'll find that evaporation increases, especially during the summer months. You would find that evaporation increase, and we'll talk a little bit more about that. We see some loss of crops here due to high winds. In the case, we have banana on the top left, then we have top right, tomatoes, we have corn on the bottom left, and we have I am not certain what that crop is. That's a tree blown down though, just to give an indication that winds can be strong enough to, even though it's not a storm, to break trees of this size that you're seeing there. Relative humidity, we are looking at the gray line across here. And you can see relative humidity in the, we live in the humid tropics, so our relative humidity is pretty much stable. It oscillates between a very narrow margin, except for when you're in Guyana and Suriname, you may have Well, their relative humidity would also be stable, but it would be higher than those for us in the Eastern Caribbean, that are a little bit further north. Relative humidity is important in that it gives us an indication of how much moisture is in the air. The lower the relative humidity is, the more the plants would need to be cared for in terms of making sure that they have sufficient water and they're not water stressed. The higher the humidity is, the less likely your plants to suffer from water stress. Other things being equal, that is. Relative humidity is inversely related to temperature, and we see that here. When your temperatures are low, your relative humidity is high, and when your relative humidity is low, your temperatures tend to be high. This is solar radiation, and by this I am talking about bright sunshine, even though plants do use many spectrum of the light wave band. So we live in the tropics, just about where the red line is. So this would give us an indication of during the months of May to September, we would have a little more bright sunshine in terms of hours, even though it may not be perceptible. And I think for those of us that are avid weather watchers and sunset watchers, we would see we have the extra hour or the extra hour and a half or 2 hours when the sun just peeps above, and still we have some bright sunshine. And so that is important in that the plants utilize sunshine to photosynthesize material. So light impacts on photosynthesis with salts and solvent. The plant is able to absorb from the soil and transfer those nutrients into the plant to help the plants to grow. So the shorter hours would slightly affect plants, but for us in the region, our hours tend to not to be as severely different as it were as for the northern hemisphere and southern hemisphere outside of the equator. So we tend to do very well on our plants managing. These graphs show what the bright sunshine hours were for 3 stations, Amisvale, Beckway, and Union Island. And the bottom one is Rabaca Strip, and the time periods are given at the bottom, 2005, 2006. And for the Rabaca Strip, 1989 to 1996. So this gives us an idea. And this is the same country, but you can see different numbers of bright sunshine. So we have brighter sunshine in the Rabaca is in the north, and the Beckway and the Amisvale Airport, that was the Met station at the time, have over 200 hours of bright sunshine, whereas Rabaca is over 100 and at times touching 200. And this is the same country, and it brings out the point that within country you could have microclimates. And these are some examples of damage which would reduce productivity. Once your crop is damaged, your productivity reduces, and this of course pans out in what's hurt in your pocket. So we see some apples here being sunburned, we see some tomatoes here, we see some banana crops, and we see some this could be anything like pumpkin or melon or something like that. So that would be the result. Atmospheric gases are not really an element per se. There are many elements. We know that plants take in CO2 as a nutrient and use it in photosynthesis. When you have high concentrations of carbon dioxide, it tends to boost photosynthesis, which spurs growth, and that's a good thing. If you are a farmer, you would like growth, and not a lot of foliage if you're growing fruit crops, but you would like growth nevertheless. And high concentrations also reduce the amount of water crop loses through transpiration. Dissolved oxygen tend to improve plant growth. For example, incorporating dissolved oxygen in hydroponics during warmer periods can improve plant growth and reduce crop time. And negative impacts have also been seen from atmospheric gases. As you could imagine, in an area where there's pollution or you have a lot of ozone, it could affect crops. And examples given here: soybean, maize, and wheat affected by ozone. In areas where there's high pollution, it would affect also your productivity. Evaporation, which is not really an element, but it's an important parameter because it considers water loss. So for us in the region, we tend to have high evaporation rate during the summer. Even though we have a lot of rainfall, we have a lot of sunshine. So it would depend, it's not high invariably. As you can see in the latter part of the year, it's the margin here changes. It depends on how much rain you get and whether or not the bright sunshine is allowed to penetrate the clouds. And you know that during the wet season, we would have a lot of cloudiness from the tropical systems that frequent the area from the African coast. So whether or not it's a tropical wave, we tend to have cumuliform clouds, which would pretty much block out strong radiation and reduce evaporation. For evaporation, this is just a reference on hot, dry days. When we have wind speeds is also a factor in your evaporation. So the higher your wind speed and the hotter and drier the day, the more you would have evaporation, as it were. If it's humid and warm perpetually, you would find the evaporation, for example, in Guyana is not as much as the evaporation for the north. To talk a bit about, I think we talked a bit about this before, so I would skip that slide and jump into what you're looking at here is DIY weather systems. So we have on the left, we have a glass jar with a graduated ruler in there, and that's done with a pen. And as long as you have an accurate measure from which to take the initial measurement, you could use waterproof marker and a jar of this kind to help you do that. We have a jar of another kind, and we see here a wind vane that gives you an indication how fast this spins would give you an idea of how the strength of the wind, and if you could work it out if you have a stopwatch and you have a reference wind speed. We have a thermometer here, and we have a wind vane here that gives you direction from wind. Sometimes it is important to know the direction from which wind comes because it may accelerate evaporation, especially if you live in a valley and the wind comes up or down the valley, you would have greater evaporation than if the wind comes perpendicular to the valley. This is a blow up of a jar. We have an 8-inch cylinder as being the larger one, and we have a smaller 2-inch PET bottle that you would drink water from. This may be a large water bottle as well, but the orifice of this has to be 8 inches. I think I have some specs later on you would look at. And then we could use this as the funnel. We need 8 inches from which the rainfall goes into the 8-inch funnel. It goes down into the bottle and is collected. And so we see graduation here on the bottle. And the bottom here, this is just for overflow and for stabilization. So you cut the jar in two and you use the bottom for stabilization and the top as a funnel. Any overflow from this bottle, so if it rains heavily, then it would overflow, and then you could measure what's in here and then use the overflow and measure, and that would give you a crude but quite reliable rain gauge if you took your time and put it together. These are some rain gauges that you could buy here in Barbados, where I am. I looked these up at a hardware store, and these are the various prices as you see here. We have digital ones on the right, and we have the ones on the left are the ones you just expose in the field by sticking them into the ground and allowing the rain to do its thing. If you notice that the orifice of the two on the left are smaller, but because these were manufactured, they are already calibrated to give you the right amounts of rainfall once it falls into the orifice for these. For wind, these are some of the, I looked these up on Amazon, and these are one of the things I've observed with electronics now is electronic items have become very affordable, and they're still for some reason very expensive for government purposes. I don't know whether it's the contractor's markup. But these are what you could purchase from Amazon. And by the way, this is a complete weather station. It has a sensor in here, and it runs from solar in this case. Yes, in both cases, they're solar driven. We have the rainfall catcher here, and we have wind speed, and here we have the thermometer, and we have the wind vane here. So it catches the important elements that you would need: wind, rainfall, and temperature. And I think those are the main ones. You could always go and find a relative humidity chart and use your temperature and wind to work out the relative humidity. So these are two examples of inexpensive stations in entirety. And as you can see, the one on the right has an app. Because it's driven by solar, you would be able to connect with it, and you wouldn't have to approach it to obtain any information from it. The temperature sensor, to expose these, and this is very important, to expose them, that is to put them in the field where they would give you, they would sense the element and give you an accurate reading. These exposure settings are standard. That is to say, when you expose it as such, you're going to be setting up an acceptable set of instrument, as it were. Once you meet these requirements, the Met Service would be well founded to collect your information because you would have met the specifications as outlined by WMO. And the National Weather Service in the US uses WMO, World Meteorological Organization standards. So the sensor must be mounted at least 5 feet, plus or minus 1 foot. The plus or minus here is that some people may not be 5 feet and some people may be 6 feet, right? So it caters for people between 5 and 6 feet, not having to do too much bending to read thermometers, because there's an error that could develop called parallax. That is when you see the bar in the thermometer either too high or too low. The ground over which the sensor is exposed should be typical of the surroundings. So you can't have an area of flatland and then you go and put the thermometer on the mango tree. That wouldn't be typical. It would have to be representative of the entire area. It must be open clearing so that the thermometers are freely ventilated and the flow of air is unobstructed. Do not install these temperatures on steep slopes, on sheltered hollow ground. So you don't want to put it anywhere that is not typical, as I said earlier. The height of any obstruction on your property, the instrument should be 4 times the height of that obstruction away from the obstruction. So if you have a mango tree that is, say, 20 feet tall, the instrument should be 80 feet away, so that the effect of the mango tree, and the mango tree would produce blockage and eddying and so on, would not affect, nor would it cast a shadow during the changing of the sun's angle on the thermometer, and so change the reading because of that. And if you have paved surfaces around, the instrument should be at least 100 feet away from the paved surface, and that's because the paved surface saps up a lot of heat, and creates a kind of heat island effect for the immediate environment, and it goes out as far as about 100 feet. I think it's less than 100, but 100, you would be safe at 100. This is what a typical Stevenson screen looks like. It's on the left. You see the holes in the side of this housing. That's for aeration or airflow to pass through so that the thermometer is in a representative but shaded area. You don't want to expose the thermometer to bright sunshine because it would heat up very fast and you will probably be reading a maximum instead of your ordinary temperature. And the height of it is about 5 to 6 feet. And it gives you some specifications here if you want to build one, and that would be quite fine. And if you notice, the color is white. And white because of the reflection afforded by that color. And we see types of thermometer here. You have one that you can simply stick in the ground. And you see this one is in a case already. The glass and the shielding is already compensating for the shade afforded by the Stevenson screen. And you see here at the top of this one that sticks in the ground, it has a gap in the cap for aeration. So we have airflow in the top, goes through and comes out the bottom. Excuse me. And we have a thermometer, ordinary one. If you build a screen like this, you simply hang it in there about 1 inch or 2 from the back, and that would be fine. And then this one now, you could simply hang it at the side of the enclosure or the screen, and that would be fine as well. So that's just a couple of examples there. For rainfall, the gauge should not be located close to the obstruction, and I would probably use the same obstruction guidance. It shouldn't be close to buildings, trees, and other obstructions because of the turbulence of wind that would affect the rainfall going into the rain gauge. To avoid turbulence, do not locate the gauge in wide open spaces or elevated sites on top of buildings and so on. So you don't want the rain gauge to be in too open an area where the wind is totally unimpeded, because the wind would just simply blow the water away from the rain gauge. So you would like it in an area that's representatively sheltered, as it were. The best site for a gauge is one in which it is protected in all directions. So if you have a grove of trees, you could remove a patch that is 100 meters, 200 meters in diameter, and then you should be fine in the middle of that. The height of the projection should not, I had suggested earlier 4 times, but twice is the minimum. Anything more than that would be fine. As a general rule, the windier the gauge location, the greater the precipitation error. Just like I mentioned earlier, you're going to have rain in the gauge, but you wouldn't have the right amount of rain in the gauge. And here we have some examples of gauge. The one at the top is one that you stick a steel holder into the ground and you simply put it in there. If you notice, it's graduated already, so you just go and read off the rainfall and you are good to go. You don't have to do anything else with that. You don't have to use, all you have to do is empty the cylinder and put it back and done. It's a 2-step: read, empty, put back. You want the bottom, you attach it to a post in an open field. As you can see, we see some sheltering across here, but in the air, the idea is to expose the rain gauge in an area that's representative. We have another one here that is exposed in a field, and this time we can see the fence in the background. That is to protect the rain gauge from, perhaps animals or unauthorized persons and so on. Okay. In the region, we have all of the information to which I alluded earlier is available to some extent. Not all countries I know may have evaporation data, for example, but the rudimentary temperature, rainfall, relative humidity, and perhaps sunshine would be available from many of the national meteorological services, who are the main providers of this type of information. In the case where you consult the Institute for Meteorology and Hydrology, they would get their data from the National Meteorological and Hydrological Services. So I would say your first line of request should be the Met services. Here we have some agromet bulletins that are provided by national services in St. Vincent, Antigua, Guyana, Jamaica, Barbados, Dominica. Trinidad has one, but I have been unable to find a contact link or a general public link on a website. Grenada has, but I have been unable to find a general access website as well. Belize has as well. So I think Guyana and Belize has been in the business for quite a while, so to Jamaica, and the other islands have gotten on board, I think, quite a few years ago, maybe 5 or so years ago. And so they would have archive data to which you could always reference if you want to go back and start your own database. These are some of the meteorological services which you can contact for information. You could either email, you could use their website, or you could telephone. The important thing is that you if you don't know what information you would need, it is best to say what you intend to do with the information. And the officers will be more than helpful in helping you to get that information that you want. You could have daily information and you archive it as you get it, or you could ask them to send you the daily at the end of the month, or you could ask them for the monthly, in which case you would have less data to deal with, and you could use those monthly to give you an annual trend. For farmers, though, I find monthly, daily information is very helpful, particularly if you ask the Met Service to give you an indication of how much rain days occur in each month. And that's very helpful in terms of planting and knowing when your rains are going to come in, so you could get the most out of the moisture and hence get the most out of your yields.